we're going to look at diffraction, or rather the application of using diffraction in a diffraction grating. Now we have the equation which you should be familiar with. It's pretty much the same as the Young's fringes, but it's in terms of an angle rather than the distance to the screen and the distance between fringes. So we have the sine of the angle, which is the angle of deviation of the light. We have d, which is the distance between the slits, and we have the fringe number, or the order. And what we will see is a set of fringes which look like this. Now there are three big differences between the regular Young's fringes that you see and this pattern that we get here, and those are these. First of all, each fringe is multicolored. The reason for that is that it's just not one wavelength of light, it's a mixture of wavelengths. The angles of constructive interference are slightly different for different wavelengths. The second thing is that the fringes are very bright, much brighter than the Young's fringes, because it's not just two, it will actually be many slits. Third thing is that the fringes are much further apart than the regular Young's fringes, and that's basically to do with the fact that since d, the distance between the slits, is very small, it must mean that the angle is going to be quite large. So let's say we have a barrier here. In fact, we'll make two small gaps in the barrier. We'll draw the normal, and what we'll do is take the light which is travelling at a certain angle theta. We look at the trigonometry of this, and if the path difference is wavelength of that light, then they will be in phase. The light from the top ray is in phase with the light from the bottom ray, so there will be constructive interference. We have a whole number of wavelengths phase difference, and this will happen at angle theta. And using trigonometry, since it's the same as this triangle here, the sine of this angle is equal to the opposite, which is wavelength divided by the distance between the slits. Now it could be one wavelength, or it could be two wavelengths, or three wavelengths. It will still give the same constructive interference. And we can rearrange that, multiply both sides by d, and this is how it's represented in the formula booklet. N lambda is equal to d sine theta. Now if we take another colour, red, which has a longer wavelength, the distance between them, for it to be lambda, it has to be a greater angle, because this distance there is actually going to be greater, so it has to have constructive interference at a slightly different angle, and that will be new angle theta. So basically the relationship is this: if we have a greater wavelength, the angle is going to be greater. D is the same, that's the distance between the slits, and this is still the first order, n is equal to 1. So a greater wavelength will give a greater angle. But white light is made of a mixture of different wavelengths. So we'll take one point here, which is the blue and the red, as we showed before. White light, as I say, is a mixture of different wavelengths. So there will be a orange line there, there will be a yellow line there, there will be a green line there, and so on, and a purple line there, violet. So what we see here will be a spectrum. So this will be the main fringe, the central fringe. Then we have this first order of constructive interference, this first fringe. You'll get a spectrum appearing there. So this is basically what you see. You have a white light source, you have a slit, you have a diffraction grating, and this will be the central fringe, which is a white where all the light is in phase. This is a first order spectrum, this is a second order spectrum. Notice the most deviated one is the red. Now the difference between this one and this one is that in the first one, the first order, that's when there's a path difference of one wavelength. This is a second order, this is where there's a path difference of two wavelengths. The long red wavelengths are deviated the most, while the small violet wavelengths are deviated less. Now, how does that fit in with the single slit diffraction pattern that we say? When we have a single slit diffraction pattern, you get this characteristic intensity curve here, where this is a first minima. But what we're doing is comparing with basically a two slit experiment. So let's change it to two slits. What you would get is separate fringes within the single slit diffraction pattern. But this is two slits. Let's have three slits. Notice that the slits get fringes get tighter. Also, there's this slight. Notice there are faint maxima between them. Let's try 5 slits. What we see here is that more slits will give more light. Also, the fringes will be brighter, and you get these weak mini fringes in between the bright fringes. So this is what it looks like. This is what the fringes look like. If it were just one color, green, it would look like this. But we have white light which separates into the different wavelengths. So this is the first order, this is the second order, and also there will be a third order one there. This is how we measure the wavelengths of light. By shining the light through a diffraction grating, we are able to use a telescope which moves around this, rotates around this disc here, and we're able to measure the angle quite precisely, so we can basically find out what the wavelength is of that light that we see at that angle. And this is basically what a diffraction grating is used for. It's basically used for spectral analysis, for getting a spectrum, breaking it up into its constituent parts, and being able to measure precisely what the wavelength is at each part of the spectrum.